So good morning. Thank you very much for being here. My name is Nazario. I'm here from monkey.org to talk about basically a topic called packet mastering. This is a talk I've been wanting to give for several years now, and I finally have it in a form that I'm pretty happy with. Kamal asked me to give a talk, and I really wanted to give this talk here, mainly so that I can teach people, start teaching people, if you will, how to write tools, for example, scanners and sniffers, such that they can do their jobs as pen testers or security administrators or other people doing audits and evaluations without having to rely on external tools. If you, for example, are a pen tester and you simply download tools off the network and you use them, run them against a target or a site, and you can inventory or categorize the results of those, that's one thing. But and you might have a decent job out of that. But if you can actually write your own tools so you can adapt to the situations and the scenarios, either as an administrator or a pen tester, you're going to have a much better position finding employment and charging more money and things like that. And basically filling a niche for yourself and for others. Secondly, this talk also comes out of the fact that many of us no longer write and release tools very widely for a variety of reasons. Where some of us live, the laws have changed such that it's a little bit unclear about whether or not we can legally release these tools anymore if we're responsible for the damage used by others, caused by others who might use them, which is a really scary proposition. For some of us, it's a matter of just not having the time to maintain them and to deal with support requests, to make sure that, for example, it runs on everybody's platform correctly. And for others, it's that we have jobs, and what we do now is basically writing and maintaining these tools, and that prevents us from releasing these kinds of tools and helping out the community. So an earlier version that I gave of this talk back in April was basically called that you too can also write your own tools. And with it, I basically told people that you too can actually be Doug Song. I work with Doug, and Doug's a friend of mine, and he's a great guy, and he writes some fantastic tools. And when you read his code, you're impressed by two things. First of all, how directly he solves problems, which, at first appear kind of simple, because he solved them so elegantly. And secondly, you're kind of thinking to yourself, why can't I do this? It looks so simple. And in fact, a lot of us are intimidated by the libraries I'm going to talk about. But this talk is only 1 hour, and I could easily go on for probably a full day about these libraries and show you how to use them. But in fact, I think a simple 1 hour introduction with the 4 libraries that I'm going to talk about here, which we use extensively when we write tools at monkey.org, shows just how easy it is and how easy it is to get started. You don't have to be intimidated, if you will, by these tools. You can start writing code like Doug Song or like others, like Niels Provost and Marius, and basically have your own toolkit, your own arsenal, and become famous if you want, or just kind of infamous if you keep them for yourself. So without further ado, I'm going to get moving here with the talk. So Kamal just entered the room, and Kamal invited me to give this talk, and I really, really appreciate it. I'm having a great time here in Kuala Lumpur. The Hack in the Box people have been wonderful. Everyone else I've met and talked to has been really wonderful. So thank you very much, Kamal. I really appreciate it. The topic, the talk is called Packet Mastering, and the topic is basically focus on raw IP internals and processes. So this is much different than socket-based networking, which is connection-oriented, where the kernel does all of the overhead for you, maintaining sequence numbers, and establishing connections, keeping state, transferring data back and forth between the applications and layers and stuff like that. Instead, you're going to be doing all that yourself. You have to fill in all this stuff yourself, decide, for example, which interface you're going to use and how to pack the packet, if you will, and actually write it to the wire and ensure that it gets out there, and even receive the data back up and make sure that it goes where you want it to. So there's a lot of overhead that you have to do yourself in this. So think about it, basically it's basically raw IP kind of, and it really is in the raw. It's networking in the raw. You have a lot of overhead to worry about yourself. Whereas in socket-based networking, the kernel and the system does it all for you. Before I continue, I have a tendency to mumble or speak kind of quickly sometimes. And again, as I mentioned before, this is a lot of material in basically 1 hour. If you have questions, please ask me to stop and ask your question to make sure it's clear. I'm more than happy to do so. We're going to be doing 4 major things with the libraries we have in front of us. We're going to be capturing packets from the wire. We're going to be capturing data on the wire. We're going to be sending some data back out as well. We're going to reassemble fragments and TCP streams, and we're going to drive this whole process as well, basically drive it forward in a very high performance and very easy to use way. And to do this, we're going to use 4 different libraries. To capture, we're going to be using PCAP. It's a widely ported and very extensible and very easy to use library for packet capture. For packet creation and manipulation, we're going to use a library called DNet that Doug Song wrote. For stream reassembly, we're going to use libnids, which was written by Nurgle, who's one of the guys in the OpenWall Linux project. And finally, to drive it all, we're going to use Niels Provost's libevent. The beauty of these tools is that they're cross-platform. They work on Linux, they work on Unix and BSD, for example. They work on Mac OS X, they work on Windows. All these platforms that you basically encounter in your daily life. So here you're not basically tied to one platform. Sometimes people will write tools and they work really well on Linux, and they may not work at all on BSD. They may not work at all on Windows. And that's fine, but if you don't run Linux, if you don't run the particular version of Linux, you're kind of hosed. So by writing code to these widely adapted libraries, you can in fact have very cross-platform code. Secondly, all of these languages are written in, all these libraries are written in C, but they work in C++ or C#, other object-oriented languages like that. They work in Python, and then at the end, if I have the time, I'll show you a Python example, how to do this. They work in Tcl, and they work in Perl, so you can go from language like C that you have to compile and worry about a lot of overhead, or you can use a scripting language, which makes it trivial to write code on the fly and to do things very easily, like Python and Tcl and Perl, which are fantastic and makes your job a lot easier. So without further ado, let's get right into it. Libevent, which is how we're going to drive the whole process, is kind of the core of basically the engine of what we're going to do here. So it's an event wrapper library. It provides an abstract event framework which wraps around poll or select on platforms ePoll on Linux and KQ on BSD. These are all mechanisms by which the system can notify a process that data is available to read or to write. We can also write once using libevent and basically optimize for whatever target platform you're writing for. So ePoll is an extremely high-performance polling interface on Linux, but it's not available on BSD or Mac OS X or Windows, for example. But libevent, at compile time, basically builds a list of what it's going to try in order. So it's going to start with ePoll on Linux, for example, and then it move on to poll or select. But it will never use KQ, because KQ doesn't exist on BSD. But on BSD, it'll try KQ first, because it's a very high-performance way to actually get data notified. So essentially, you're writing once, and you've optimized everywhere, which is a really fantastic way to do this, right? So at compile time, libevent's basically optimized whatever platform someone's going to be compiling your code on. Libevent can also handle signals and alarms received and run off actually on the program as well. There are 4 key steps to using libevent. You initialize the framework using event init, which basically sets up the internals of the library. You create an event using event set. So you basically say how, what you would like to look for and how long you want to check in each round. You then add it to the list of events to check, which is going to be run. And then finally, in event dispatch, you kind of say go, and it sits there and loops over those events for the whole time. A main event loop basically looks like this. There's only 4 shown here. You can have as many events as you want to, and you don't have to have all of them. But ultimately, these are the 4 main event types you're looking for. So we start here at the top, and as we go clockwise, in this case, we're going to look for a readable condition on a file descriptor. So can we read data, rather, off a file descriptor? So for example, if a socket has received data, it's waiting for us to read and to process. So is that file descriptor readable? If it is, great, we're going to handle that. Otherwise, we're going to move on to the next one. In this case, is it writable? Can we actually write data to that socket? Can we pass data out from our program? Have we caught a signal? It basically has an external process or external system basically notified our program of some sort of condition using a signal, a very lightweight inter-process communication mechanism. And finally, has an alarm gone off? So has a timer that we've set up basically expired and some sort of condition's been met? And you can basically loop around this all you want. You basically wait at each of these for some period of time, a few milliseconds or even a few seconds if you really want to, before you move on to the next. When you catch one of those, when you catch an event, you execute a callback associated with that. So and then you return back to the loop once you've completed that. In the callback, you pass data up to the event handler that's been caught in the event, in this case, data that you want to write to a file descriptor. So in this case, we have a writable event. We've caught the writable event. We can actually write to the file descriptor. So we execute the callback where the data is basically written to the file descriptor, and you return back to the main loop. In libEvent, it's important to do one of two things to keep the event loop reoccurring, because ultimately you want to do this more than once. You either have to schedule the event initially with event add, using the evPersist flag. Basically it's a persistent event, or you have to manually re-add it. evPersist actually is broken currently, I think, in libEvent, so I just manually reschedule them at the top of them, making sure that it works each time. So a lot of folks will typically use thread-based programming as a way to achieve high-performance programming. Threads are excellent, but events are just as excellent as well, and I think have a number of advantages over threading in most cases. As I mentioned, they're both used in high-performance programming. A lot of people typically associate a requirement for using threads if they want high-speed, high-performance code, especially with packet-based actions, but that's not always the case. In threading, you're going to spawn a thread for each task. In this case, you have a reader thread, you might have a writer thread, you might have multiple threads that are writer thread, for example. You might have a processing thread or multiple processing threads. So you spawn multiple actions and threads within the program itself. Any thread can basically be blocked on a condition until it achieves what it wants without basically stopping the whole program overall. That's the whole point of using threads, right? Because you don't want to actually block the whole program. However, threads are really difficult to debug if you ever encounter a problem, and it's pretty easy to encounter those problems. You have to basically know the global state of the program and in the state of each of those individual threads to understand what just happened there. So, for example, a deadlock condition can occur where two threads basically have requirements upon each other and can't move past this until they basically achieve some sort of condition. They're basically deadlocked, so they're stuck. You have to basically know the state of the whole program overall, the state of those threads and what they want. And again, digging into that with GDB, for example, is a little bit difficult. Not all threads not all functions rather, in the C library are thread safe, meaning that if you call them within a thread without properly protecting yourself, like using a mutex lock, you can in fact clobber data in there. So malloc on Linux, for example, I think is not thread safe. So if you actually malloc data in one thread, if you malloc without locking your malloc mutex, you're actually going to clobber the data because you might malloc the exact same region or part of the same region. So here, two threads think they have individual data portions to write to using malloc, but in fact they overlap. You're going to clobber data when each of those threads reads and writes. And ultimately, this is a big dance you have to choreograph here, and the onus, the impetus to do this correctly is on you. So it's really easy to mess it up. When it works really well, and some people and some platforms are fantastic for threading, but it's really difficult to get it right. In event-based programming, however, you have a main, as I mentioned before, you have a main event loop, you have a main thread of execution, which loops over these possible actions. Can it read, can it write, has it caught a signal, or has it caught an alarm? So, and each of these actions has an associated callback mechanism, which basically processes the data on that condition. It's very easy to debug because basically you have one thread. You look at the file descriptor that's active, you look at the callback that's been called, and kind of step back from you basically backtrace. It's very easy to basically process, figure out what state you're in, what data is globally available in the program. Deadlocks don't happen because this is non-blocking. As long as you return from your event handler, you're just fine. Because it's never covered by a straight thread. There's only one thread of execution. And your program is always either doing something or is looking for something to do. So it's a very, very efficient way to program. And in fact, this is what I prefer to do in most cases at this point, is to use event-based programming. And so this is why I encourage you to look at it as well. And also encourage you to think of high-performance programming as not requiring threads. It can in fact be done using events. Where I work, we actually do all event-based programming as opposed to thread-based programming. We're processing hundreds of thousands of events per second on very simple boxes, just using good data structures and good structures of our events. It's ultimately what it comes down to. So now let's move into PCAP and libdnet and even libnids. So this is just a reminder of the networking stack. You have layer 2, your link layer, you have your IP layer or layer 3, and then you have layer 4 and above with TCP and the data associated with that, or UDP, and so on and so forth. At the link layer, you might have, for example, an Ethernet header structure with a source and destination address and an Ethernet type. Is it IP, or is it ARP request, ARP reply, and so on and so forth. An IP header structure with various fields available to it that you have to basically check or fill in yourself as well. You have, for example, the TTL, you have the protocol, which tells you what the next header is going to be, and so on and so forth. This is an IPv4 header. IPv6 is a little more complicated and extensible, but you get the idea. Here's a UDP header. Should be very familiar to most of us as well. If not, this is a great time to learn it. You have source ports and destination ports, of course. The UDP header is very simple, very straightforward. 4 main fields, and then you have the payload, essentially. TCP is a little more complicated, but again, source port, destination port, sequence and acknowledgement numbers. You have flags, you have lengths, you have optional urgent pointer data, optional options, so on and so forth. The checksum, of course, in there. And I mention this because when we capture these packets, or we process these packets, we have to think about all these fields, how we want to fill them in, or how we want to read them. So libpcap is an excellent packet capture library. What's great about it is it's platform independent. It's been ported, as I said, to Windows, to Unix, Linux, BSD, all these things, and it basically provides this abstract way to get at raw sockets and basically the data on the wire. It's very basically industry standard, so if you actually write programs using libpcap that can read or write pcap data, you can exchange data with almost anybody out there in the world doing this as well. There's a number of packet capture utilities out there that are platform specific. They're extremely efficient, even more so than libpcap. However, they're very locked into a particular vendor or a particular platform. It's somewhat difficult to actually process that data around. libpcap is it's obviously very extensive, very flexible because of that. It offers pretty decent performance. It's not as great as it could be, but it's not too bad. On Linux, for example, they made some optimizations to it in libpcap that actually speed it up much compared to, for example, the BSD. There's BPF on BSD, which allows you a pretty decent structure, but it's been optimized. So zero copy BPF, for example, so there's no you don't have to incur a copy overhead when you receive a packet, for example. The order of operations in PCAP is very straightforward. You create a PCAP object, which is associated with the device and basically with the file descriptor, and sort of options set on that. How much data you're going to capture at each routine, is it promiscuous or not, and so on and so forth. Then you basically process data from that by basically executing a series of callbacks, which I'll show you in just a second. And when you're done, you basically close the object. It's all in C, but it's basically object-oriented programming, right? You create a PCAP object, you use it, and you throw it away when you're done. This is basically how we get data out of PCAP. There's 3 main routines here. So there's PCAP loop and PCAP dispatch, which are basically the same routine underneath, just a slightly different API between them. They're event-driven, meaning so when packets arrive, the callback is executed. And you receive, as shown in green here, the PCAP packet header, which contains information like the time the packet arrived and PCAP information associated with that. And then the packet, which starts at layer 2 and above. So Ethernet headers, for example, and then the IP header and the TCP header, for example. This is important because you have to basically walk along this and figure out which data you're looking at. PCAP next is a somewhat different one, but it basically returns to the next packet that PCAP saw as a buffer. And so it's up to you basically to loop over this indefinitely. But ultimately, what you're really doing is getting back packets, and you have to process them using a callback routine. And as I mentioned before, you have layer 2, 3, and 4 and above that you have to look at for this packet. libdnet is just quite the opposite. You basically write packets out to the wire or you manipulate them. It's a very simple interface, and again, like PCAP and like libevent, it more or less is optimized to the platform that it's been compiled for. It's been ported to all 4 major platforms: Windows, OS X, Unix, and Linux. And it has a very relatively easy to use interface, actually. It's consistent, it's well designed. It's Doug Song's library. He's been writing this code for years, and in fact, it's kind of bubbled up as this is how it's going to work, and it works out pretty well. In the case of writing data to the wire using an IP handle, you open the network object using IP open, just like PCAP, right? You end up with an object. And you manipulate it. So you allocate packet memory, you construct the TCP packet, you construct the IP packet, and you checksum it. Otherwise, it's not going to get very far out there. And you write the packet using IP send, which is associated then with the IP object that you have. And when you're done, you close the object, you throw away the memory, and you're all set. DNet goes well beyond this, though. So that's just the IP interface. It can actually handle IPv6 as well. It can handle arbitrary IP addressing, both IPv4 and IPv6. It can handle ARP. It can handle, so for example, you can not just add and delete entries, you can loop over them, you can create requests and replies and stuff like that very easily. Very standard interface. You can change the routing table on the fly using a very simple interface in this library as well. You can change your firewall rules. It works on BSD, Linux, OS X, so on and so forth. Very simple. It's kind of a primitive interface, but you can basically add firewall rules as you need to or delete them. You can create Ethernet packets, just like IP packets, but again, you're on layer 2, where the onus is on you to address it correctly and fill it out correctly. You can change your interfaces, so you can check, I can even set the addresses on them, set the options on the interface, add aliases, delete them as you want to. You have arbitrary binary objects called blobs. And finally, you can have a decent pseudo-random number generator, which allows you then, for example, to easily pass some data out. I've been asked to request that anybody who's going to participate in the CTF competition go to the registration counter immediately. I think the CTF is about to begin shortly, so they want to make sure everybody who's ready to go is going to be involved in that. So thank you. Please go ahead and, if you need to, go ahead and go play the CTF. So on the right here is basically kind of an abstract TCP header that we showed you earlier. Doug has provided a nice macro to basically pack the header. It's just a structure, right? So it's just structured data. It's up to you then to fill it out, but this macro does it for you. It fills it out pretty correctly. So for example, you have this header object here, and then of course you fill out the source port, desk port, sequence number, acknowledgement number, and so on and so forth, right? You basically set your packet this way, and you returned a TCP header. And it's good to go. Basically, you can write it out as you want to. There's one for IP pack header, there's a UDP pack header, and so on and so forth. But very simple ways to basically create packets on the fly with having to worry about filling out the structure manually. It does it for you. It sets the byte ordering correctly and stuff like that. One of the things that sometimes people forget about is is comparing IP open to ETH open. So IP open returns an IP device, and you have a question?
I think it's request.
Oh. Okay, I'll try and slow down a little bit. Any specific questions at this point that I should go back over real quick? Okay. One of the things that people often forget about is IP devices versus Ethernet devices. There's kind of a subtle distinction here. So you're both having access to writing to the network, and the order of operations here basically shows you what you would do. So in the fixed width font is basically how you, as a programmer, would access this. So you'd open the object, either IP open or ETH open. You would create the IP packet and checksum it, of course, and then you would send it. And what the system will do with an IP packet, with an IP object rather, is it'll actually do a routing table lookup, find the appropriate interface that needs to go out on to receive the data back to it, and then use that interface. Whereas ETH open, you had to specify a device that you want to associate that with. So for example, IP open doesn't really take an argument, but ETH open could say, open me my FXP0 interface on a BSD system. And it'll actually use that. It doesn't matter if it's the right interface or not. It doesn't do the routing table lookup for you. IPSend does it for you. So it's important to remember that if you want to, for example, ensure that you get data back in that interface, an IP open is a great way to do it. More importantly, what IP open versus ETH, what IP send versus ETH send will do is IP send passes the packet at the IP layer through the kernel, which the kernel then fills out the Ethernet portions of it. So the source and destination addresses are filled out correctly. The Ethernet type is also filled out correctly. When you use ETH send, however, you actually had to pack the Ethernet header as well. So you had to fill out the source and destination addresses, and you had to fill out the type correctly. And if you don't do that, then basically the packet won't, for example, the packet won't go to the destination, or it won't go to your desktop router, for example, your default router. And finally, the packet is sent at the end of this here. But there's a very subtle distinction here that if you're not aware of it, will basically fail and with ETH open. Not because the library itself has failed, but because you didn't do all the things that you had to do in the first place. So also, if you leave off the Ethernet header, for example, you just send an IP packet and ETH send, it'll assume that the first 32 bits are actually part of the Ethernet header. So it'll trample the whole IP header for you. It'll basically ignore it. It's just garbage. Putting these all together, so I really, as you guys can see here, I really tore through those three libraries there. So if you guys have any specific questions, now's a great time to ask before I show you how they go together. So JScan, J is for Jose, obviously. It's a TCP SYN port scanner. So it's nothing special, right? You can do this in Nmap, you can do this in ScanRand, and I think every script kiddie has written one of these, or everybody's used one of these at this point. It also allows you then to do OS fingerprinting, basically by looking at the traffic that comes back to you. So you can look at the packets and make determinations of what the operating system is likely to be on the target system. You can also do passive port scanning, because it has a listener component to it as well. And so if you can watch traffic go by, you can tell what ports are open, even when operating systems are available on those remote systems. And of course, it's an active port scanner as well. But because it has two modes to its operation, you can actually decouple it. So for example, I could take my laptop here and say, spoof my home address back in the States. So traffic will leave here and be written out to the network from my laptop with a source address of my system back home in the States. And if I have a listener over there, which is basically listening for arbitrary packets coming back in, the traffic as it hits the destination will wind up going back to the States, not back to my laptop here in KL. And so then it will receive the data there. So I can kind of have multiple senders around the world all going to one destination. So you can kind of basically spoof your sources this way and get the data back very easily. Software is on my website. The URL is at the bottom there, and it'll be at the end of the talk as well. JSCAN operates very simply. It opens a PCAP object for receiving the data. Either the active scanner needs to receive it as well as the passive scanner. If you are an active scanner, then it opens an IP object from libdnet for sending the packets back out. You then create and set the send and receive events. So using libevent, we're going to drive the whole program here. So we're going to create the receive event, which basically associates the PCAP file descriptor with the readable condition on it and the callback associated with processing that data. And the sender one as well, right? So if we can write to that descriptor, then we're going to execute the callback to send the packets back out. We have a send and receive callback. The receive callback actually can also optionally fingerprint the packet that's been received to fingerprint the OS. It also reports the results to you in kind of a pretty fashion. And the system will then loop until all the ports have been scanned or you've stopped the passive receiver. I'm trying a method of showing code which kind of basically fits pretty well on a single slide by highlighting what's interesting. The method comes from Hansen. He's written some fantastic books this way. So if it works, it's great. If it doesn't work, please tell me. So I stopped doing this. What's written with the angle brackets is basically code that I would show you in another slide or another section. So it's not quite straight C code, but you get the idea. You can kind of plug in each slide into each of the spots and kind of get the program itself. So here's the main body here. So the CTX object here, the CTX object here is basically my context. So instead of keeping around a bunch of globals that describe, for example, the PCAP object, the IP object, the random number generator object, the port I've scanned, and all those kinds of things, and the flag for the scanner, what I do is I basically pass around a context object, which is a structured object that basically has all those members inside of it. So I set the rand object within it to rand open. So rand open is from libdnet, and it opens up a random number generator. And this allows me then to access very specific types. So for example, I can get a random short integer out of it as well. The P object within the context is a PCAP object here. So I'm doing a PCAP open live. What PCAP open live does, What PCAP Open Live does is it opens a live network interface. There's another one that's very similar called PCAP Open Offline for opening PCAP save files. So if you've actually dumped your traffic to a file to pass around or store for later on, you can then open it that way. The interface is an option passed through getopt, which I'm not going to describe here. So for example, you can say -i fxp0 or -i eth0. So it'll open the appropriate interface. 1500 is in this case the snapshot length of the packet that's going to receive. So it defaults, I think, to 96 bytes, or 68 bytes rather, which may not be enough if, for example, someone's padded out a bunch of options in their packets. The next option here, where ctx.flags equals scan flags passive, the flags member object of the context object is basically just an integer telling me, did the user want a passive scanner or an active scanner? If it's passive, it has to be in promiscuous mode. Otherwise, it doesn't have to be in promiscuous mode because the traffic's coming right back to it. And so this is a zero. This is a Boolean value, a 1 or a 0, basically telling you whether or not to open the interface in promiscuous mode, meaning you see traffic not destined for yourself, but for other people as well. 500 is a timeout in milliseconds that the PCAP object is going to wait to come back to the main loop of execution, telling you I've seen traffic or not. And eBuff is the error buffer. It's just a character buffer. If in case there's ever an error, it basically spits out that error. That's where the error gets bubbled up. So, for example, it'll tell you you don't have permissions to open the object, the interface doesn't exist, I've totally failed for whatever reason, and so on and so forth. And that's what the next line does. It just makes sure that the PCAP object, the ctx.p, really exists. If it's null, we error out and we quit telling the user that something happened. The next one, the DL lane, is actually PCAP DL off is not a standard PCAP interface. It's a standard PCAP call. It's stolen from Doug Song's code. Basically, what he does is he looks at the, in the routine, basically, you look at the PCAP object and you find out, is it an Ethernet interface, is it a PPP interface, SLIP interface, and so on and so forth. And this returns the offset of the layer 2 header, how long it is. Is it 32 bits? Is it, 48 bytes or whatever? Telling you basically how much you have to skip over for that header length. I'll explain the event setup on the next one here, and then at the end of it here, you basically say the scan was completed to however many seconds, and the program exits the status of 1. This is the event setup. So basically, slip this slide here in the event setup line towards the bottom there. So I initialize the event framework with event init. This is from libevent, and in my context object, I have time values, basically telling me how long each event is going to wait before it moves on to the next event. So in this case, it's 500 microseconds. Not very long, so it can kind of basically have very fast scanning here. Because libevent only operates in file descriptors, I have to basically get the file descriptor out of the PCAP object. The PCAP object contains a number of things, including the file descriptor describing the interface it's just opened, but it also contains who opened it, how much they're willing to wait, how large is the snapshot length, and so on and so forth, the name of the object, the name of the interface rather. And so all we really want out of that is a file descriptor. So we use PCAP file no, which basically returns just that value, because libevent can't operate on just abstract interfaces. It only works in file descriptors. I then set up my receive event. My receive event is going to work for both an active and a passive scanner, so there's no conditional here. But in my context object, I have the receive event, which basically holds the structure for a lib event, describing when you receive on this, when you receive data on this file descriptor, do the following things. The PFD is in fact the PCAP file number, the file descriptor rather, describing the PCAP object. So this is the read and write object, or the file descriptor rather. The condition that I want to in this case is look for reading. So event read, basically saying with this data on this file descriptor, please report back to the callback and pass the data up there. Underscore receive is the name of my receive callback. And finally, I can pass an argument to this callback. In this case, I pass my context object. The reason I do this is, as I said, so I don't pass around any globals, but every piece of code can get added, in fact. So in this case, you're basically passing up an optional argument to my receive callback here, which you'll see in just a second. And then I add it to the event list of things to loop over for. So here I add the receive event, and I add the time value, basically saying wait about half a second or so for each of those. If it's a passive scanner, then I have to open up the IP sending object, right? So IP open, and I set the context to that and check for failure. I then set the event for that as well. In this case, we're going to do event write, ev write here for libevent, basically seeing if we can write to this. Then we're going to call the send method, or the function rather, and again, pass the optional argument of the context back up, add it to the list of things to do, and we initialize our destination port on ctx.d port at 1. It's not a very great scanner, right? It scans from 1 to 65,000 straight up, so it doesn't really randomize the ports, but it's just example code. And then finally, we dispatch. We do event dispatch. And what this says is loop indefinitely over all these events and return when you're done with events. So here's the receive callback. And again, you can basically see what just happened here, right? So if there's data to be read on the PCAP file descriptor, what libevent does is it basically calls this receive callback, because this is what I set up on the previous slide with event set, call underscore receive. And it has 3 arguments: the file descriptor that was being used for the event, the event number, in this case a short, which we don't really care about, and the optional argument. In this case, the argument is my context, so I cast my argument to my context. And in this case, if I just basically check to see if I have to reschedule the event. Otherwise, it gets called once, gets removed from the queue, and that's it. I have to reschedule it in this case because I want to loop indefinitely, unless, of course, I'm done scanning. And here, then I call pcap next. So we've kind of mixed libpcap and libevents here. So pcap next returns only the next packet that's ever seen. In this case, we're waiting to kind of, we know that we've got data that we can read on this. This is our receive callback. We've got data we can read on the pcap file descriptor. And so we return it with pcap next. And then we call report on this. Report basically, you'll see in just a second. And then at the end of this, we just return. Send is basically exactly what we expect it to be. Kind of it's quite the opposite. Again, it's got the same interface to it. The int file descriptor that was being used, the short event number, and an optional argument, which again we're going to pass as my context object. In this case, we have to reschedule unless we're basically done scanning. So event add, we just basically have to re-add it. Notice that I don't have to call event set again because the event is already set up. So I don't have to reinitialize memory and reinitialize all the variables there. I have to re-add it. The event still is valid. So then I create a packet here. So the JSCAN packet is just a structure that describes the union of an IP header and a TCP header. So we fill it out. So IP pack header is that macro from Doug's code, which basically fills out the IP header here using a variety of things. So we set the type of service to low delay. We have a length that I think is fixed size. It's just 40 byte SYN packets. We then use a random source and destination port, random source port rather, but the destination port is in fact fixed from our scanner. We're going to have a TCP object here, in fact, and so on and so forth. We fill out the source and destination IP addresses here as well. And we pack the TCP header much the same way. Again, it's a JPacket TCP header. We fill out all the information there as well. And we checksum the packet as well. IP checksum is pretty smart. It's a routine from libdnet. It basically, it'll checksum the IP layer, and if it has to, it'll checksum the next layer as well. It's very smart. So for TCP and UDP, it'll do the right checksum, and so on and so forth. For example, a GRE packet doesn't have any checksumming at layer 3, so it doesn't have to do it. So if they basically call it repeatedly, the TCP and then the IP header as well, you just call it once, and it basically walks through the packet. And it does it in place as well. So the packet it doesn't have to be, nothing returns from it. When we send the packet, we send it out the IP object that we opened initially as well. We then increment the destination port because we're port scanning a single box. We're going to walk up the ports from 1 to 600,000, and then we return. We're done. This is where it gets kind of interesting in the reporting phase here. So this is directly called back by the pcap next routine. So pcap next returns this packet, and then we basically pass it out to report. So we have a ucar packet here and an optional argument. And again, I'm passing in my context object because it has a bunch of useful information I need to know. So you guys follow me along here? Is this clear? Please stop me if it's not clear at all, okay? Hopefully all of you understand C code or understand the basic gist of it here. Basically what we do here is we're walking the header here. So remember that I said earlier on when pcap returns, it returns everything from layer 2 on up. So layer 2, layer 3, and layer 4 on up. We don't really care about all the data at layer 4, so 5 through 7 we don't really care about. What we care about is layer 2 and layer 3. We actually don't care about layer 2, we care about layer 3 and layer 4, so the IP and TCP header here. So we look for the data link length, which is stored in our context object, basically walk the pointer, which describes the packet past that, because we don't care. Which is kind of risky here, because we in fact could get a packet that doesn't really map to an IP packet. But it's example code, and it's poor form, so you should fix the bug if you use the code. The code's all BSD licensed. It's on my website. Download it, fix it, have fun with it. So then we make sure there's an IPv4 packet. If it's not, we bail. It doesn't really matter at that point. We then look at the source address. So then we store it basically as a character pointer, just a string. So because we're going to print it out in a second. If it's not a valid source address, we also bail. So these are two simple little checks to make sure that the packet we received is actually an IP packet, as opposed to just some junk on the wire. The comment here basically describes what we're about to do on the next page here. If it's a passive scan, we don't really care about the source address, right? Because we want to watch all traffic go by and kind of get an idea of what websites are running, what the AIM server is running, that kind of thing, right? We're basically watching all sorts of traffic go by. It's not just our traffic, not just our scanner traffic. However, if it's an active scan, we only care about our own packets here in this case. We don't want sort of stray junk filling in there as well. So we make sure that it was the destination address that we specified. We also make sure that it's a TCP packet and we have SYNAC set. Because we're sending SYNs, we only care about SYNAC for open ports. We don't care about reset packets. We don't care about drop packets as well. So that's what this next conditional does. The top 3 lines here basically do that. If it's a passive scan, we make sure that it's addressed to us. If it's an active scan, rather. Otherwise, if it's a passive scan, we don't really care. And we make sure it's a TCP packet. So we look at the IP header through the IP protocol pointer, the structure member there, and the IP header. And if it is, then we continue on here. So we look at the TCP header. We basically we walk the pointer and cast it again into a TCP header. And we then look at the flags. If it's SYNAC, keep going. We're set. Right? We have an open port. So struct servent is just a structure describing a service entry in Etsy services. So basically, when we can print out the service name very very prettily instead of just reporting a port number. So that's basically why we have that there. I'm not going to show you the OS fingerprinting code unless you guys really want to see it, but it basically passes up various attributes of the TCP and IP packet up to this, so it can get a description essentially of the packet and make a determination based upon the database of what it's likely to be the operating system. We then call get service by port with both the port number and the protocol number. So we get, for example, we map port 80 TCP to www, which is nice, just by using the Etsy services file. And we finally print it out. So this basically pretty prints it here, this big printf line here. Make sure that it's nice and legible and looks pretty. And finally, we're done. So the output of JSCAN is shown here. The first one is actually a couple lines showing the passive scanning that goes on. So JSCAN-type passive. I'm using the FXP interface on my laptop. And we're going to fingerprint using the pf.os file. So scan started, great. Here's an address, 192.168.159.40. We don't know the operating system it's running, but we know that it has port 80 TCP open that maps to www. So the www comes from the get service by the get service entry by port, and we report 80 TCP. That's great. The next one, however, we know is a FreeBSD box because we've actually fingerprinted it using the attributes inside the IP and TCP packet. It's fantastic. The next one basically shows an active scanner. So here, it basically walks all the ports on a single system, reports it back as a Linux 203 something box, and shows us what ports are open. The reason I chose to list what each port and as far as the operating system is concerned is if the box is doing NAT or is a bridge or something like that, is redirecting specific ports to different boxes. So for example, you might have a Linux box back there, you might have a Windows box, you might have a Mac OS X box. You get to see that. So it's not just one port mapping for the whole IP address. The IP address can actually be masking multiple a bunch of different boxes back there. Using JSCAN, I've actually found some interesting stuff. It turns out that MSN, the Microsoft organization, actually uses a bunch of OpenBSD PF firewalls in front of the web servers. So all sorts of neat stuff like that just pops up with just watching all sorts of traffic out there. So in this case, this is a box you have lying around. It runs a bunch of stuff, and BGP, for example, in this case. So it shows you basically, it's kind of pretty in the sense that it's sort of readable, but it shows you kind of the power of a very simple scanner. This is like 400 lines of code. In 3 libraries, basically, right? So it shows you how you can write a very simple and pretty fast port scanner as well doing this. Any questions about JSCAN or the 3 libraries I described there? Okay, one last library. This one is called libnids. It's written by a guy named Nurgle, and when Nurgle was running for his master's project, what he did was he took the Linux 2036 stack. Remember Linux 2.0.36? It's a great kernel. Man, they're up to 2.6 these days. It's great. What he did was he basically took it out of the kernel and put it in userland. So you now have access to a TCP state machine, an IP state machine actually, so it handles not just IP and TCP and UDP. It reassembles fragments correctly, just like a Linux box would and stuff like that. This is fantastic for a NIDS e-box or an event generation box generating data on the wire. Uses libpcap. Internally, it uses libpcap to capture the data and libnet to basically manipulate the addresses. Libnet's basically like libdnet, but I just tried not to describe it. I think that libdnet has an interface that's a bit easier to describe to people most of the time. But the really cool thing about libnids is it does all this fragment reassembly for you. You don't have to bother trying to figure out, oh, I have to, it belongs to this packet here. Oh, it's finally built together, and I can now shove it out. It does it all for you. So as I described, basically Nurgle took, normally the IP stack just lives in the kernel. You don't have your own stack in the user LAN, and he threw it out there in user LAN using libnids. It's a receive only. You can do some sort of outbound connections, but nothing too much. So you don't have a full IP stack out there. You don't have like a user LAN connector or something like that, but you do have access to a bunch of different methods. Libnids looks really intimidating, but in fact it's dead easy to use. You, again, initialize using nids events, just like we did in libevent, rather. You initialize a framework. Fantastic. And then you register function pointers. The function pointers basically describe how you're going to handle all sorts of conditions that the program might see. So the three main ones that we typically see are TCP, IP, and UDP. So it internally handles fragments for itself and it puts them back together and tells you, oh, that was a fragment of the TCP packet. Here's the TCP stream. And then you run, and nids run is really cool because what it does is it's all internally event-driven. Just like our scanner was event-driven, we had to basically bring in a whole different library. This actually runs internally, so you just call nids run, and it goes and goes and goes. And you can even react with it. So, for example, if you see a condition that you don't like, you can actually call nids kill TCP, and it'll actually send out the right package to shut down the connection arbitrarily. Pretty cool stuff. So you have these callbacks associated for protocols. In this case, the three major ones are TCP, UDP, and IP. TCP callback gets actually a TCP stream object. So TCP is bidirectional. So you have client data and server data, and you have all these attributes available for each of these. You have a sequence number and stuff like that. You have the number of bytes sent and the number of packets sent and stuff like that. It actually has a TCP stream object. So you basically call within that object to get the parameters out. You say this. So for example, you have all the payload strung together, just like it would see on the wire, but it's actually put all together for you, so you have access to the stream data as well for both the client and the server, and it's split out, client and server, so it's not intermingled. Fantastic way to do it. The UDP callback gets, I think, 5 things back. You get the source IP and the source port, the destination IP and the destination port, and the data that was actually inside the UDP packet. Very easy interface. And the IP callback just basically hands you an IP packet that's been reassembled, so you can do all sorts of checks and balances on it. I'm going to illustrate it here with a program I wrote called JFlow. What JFlow does is it basically builds PCAP to NetFlow summaries. So you have this, you can monitor your network using, in this case, libnids, which basically watches using libpcap, which we described earlier, and it builds NetFlow summaries. So NetFlow summaries basically describe the connection in kind of a one-liner, basically saying from this host to this host, on this port to this port, on this protocol, I saw so many packets being sent and so many bytes being sent. Really great way to actually monitor your network in a very lightweight fashion. It can demonize, so you can kind of run it in the box and have it spit out data to a remote system. It's compared to a real NetFlow generation system. It's not very lightweight. One of the things I didn't do actually is build on timers and stuff like that. And also, it's pretty inaccurate because of the way that libnids reports data back up sometimes for packet counts and stuff like that. But it shows you basically how to have a very lightweight PCAP to NetFlow tool, right? Just using libnids. And again, it's on the website here. Excuse me. So we have a very simple main, right? The key things here are we initialize, we register an IP callback, and we run. Basically, let libnids handle itself just fine. And we have 3 or 4 different things here, right? So we have a UDP socket connect. Big deal. I don't think you need to see that. The IP callback is what gets called from nids run whenever it sees an IP packet, and it throws it back up in there, and then that's a handler for it. And then finally, we export the record in NetFlow format. So this is the IP callback here, and again, struct IP packet is all it hands up, just an IP packet as a structured thing here. And so basically what we do is we tear apart the packet to build a NetFlow record here. So with source address and destination address, the next hop address of the router. We actually zero it out because we don't really know where it's going to be going for the next router. We don't have access to that data, but a real router or a real switch would. We don't know, we don't really care. It's just examples, right? Number of octets that were sent back and forth. The source nation, if it was TCP, the source destination port we'd care about. If it was ICMP, we'd care about the type and code and stuff like that. And then finally, at the bottom here, we're going to export the record. So we basically fill out the header of an IP, of a NetFlow packet and send it out there. And that's basically it. But ultimately, coming back here to the main, this basically shows you this big, huge library which does all these really cool things for you is actually really easy to use, right? So within 3 or 4 lines, you've actually got a fantastic up and running system here. And it's basically just tearing apart the structures of the IP packets and filling them into the structure of a NetFlow record, and just writing it off. Very simple to do, but kind of powerful, and all the same. Well, that's the beauty of a library like this, is that it's basically made it really easy for you to do very powerful things, very hard things to do. And so then you can worry about more interesting stuff, like how do I make this run really fast? What do I place in the network? How do I get interesting data out of it? As opposed to the engineering problems of reassembling streams and stuff like that. So this is what flows look like when you visualize them using TCP dump. It's not terribly pretty, but you can basically see a TCP summary here and an IP summary here as well, and so on and so forth. Basically describing a connection summary here. For the company I work for, processes a bunch of this stuff for a bunch of people and basically builds models of networks based upon this data. So you can do a lot of interesting stuff with NetFlow, but this is a very simple way to generate those kinds of records. So as we draw to a close in the talk, I want to talk real quickly about some sort of performance considerations here. In JSCAN, one of the things that I do is I basically keep a list of all the IPs and ports I've seen over time. And if I've seen it before, I don't really care. The problem is traversing a list is ON, right? So it scales linearly with a number of times, with a number of things that are inside the list. So after a while, it gets really, really slow. Obviously, if you're running this on a very large network or a very fast network, it's going to get slow very quickly for you. So you want to think about a much different object here to actually store this information in. So just because you know how to write code in PCAP and DNet and stuff like that, you still have to think about real basic CS type fundamentals here to improve your code, right? So that's actually where all the joy and beauty of optimizing the code comes in, is thinking about the real CS here, having to actually really do the hard work there. Also in JSCAN, there's a loop as you fingerprint these packets, and each time inside the loop, you open the file describing the operating system attributes for the TCP traffic. You have the malloc, which is somewhat expensive after a while. You have to parse the file for each of these just to make a determination of what that packet mapped to as an operating system. Again, as you see more and more packets on a network, in a very high-speed network, this gets dog slow. It'd be much, much better to map this one time initially and just call back into it. So again, structure of your code matters a lot as well. And you can profile your code using like gprof and stuff like that. And OS 10 actually has some fantastic profiling tools to show you where the slow spots are and basically think about how to improve that. Especially when you're doing high-performance networking, you have libpcap, which is pretty high performance, libdnet, which is pretty high performance, and libevent, which really drives it very quickly. But if you do, for example, these kinds of things like I did here, a singly linked list in this loop which has to do all these operations, you're killing yourself in performance. It doesn't matter what else you're doing. And finally, when you're really, once you've gotten down to some once you've optimized away all the really basic stuff, like you've moved away from lists and moved over to hash tables, and you've actually, mapped stuff correctly the first time and malloc inside a tight loop, then you can start worrying about other things. If you're dealing, for example, with gigabit networks, the interrupts on I386 get to be a real bitch, real fast. So each time a packet arrives, right, on a fast Ethernet connection, the processor has to interrupt. So whatever it was doing gets interrupted to receive the packet and shove it in there. So GigE is going to actually coalesce these interrupts together. So for example, you might have 10 packets arrive and then only one interrupt to pass them back up. So this is a market improvement, but again, unless you really optimized your code, it doesn't matter what kind of hardware you throw at it, you're still slow inside the code. Hardware checksumming is also very important when you think about GigE speeds. If you can offload out of the main processor, out of the CPU, onto the card, for example, even out of this narrow memory bus, if you can keep it over there to throw away packets that are just going to be garbage in the first place, if you can check some of those on the hardware of the card, you're set, you're golden, you've saved yourself a few cycles. And finally, real good memory management for high-performance networking gets down to things like pool allocators and slab allocators. So malloc, when you actually look at it inside the kernel, is somewhat slow, because you have to actually do a bunch of stuff inside the kernel. So if you call this repeatedly, and in fact it's very slow, what pool allocators do or SIB allocators do is malloc once, and then in userland allocate the map, or just manage the map of who owns what inside there, how, you know, where it starts and how long it is essentially. So you don't have to basically keep mallocing inside this loop, which causes your system to get really, really slow really quickly. So don't worry about these kinds of things until you solve these main problems here as well. So a lot of folks will think about, for example, oh, I need to get a bigger, faster box. I need to have a much faster hardware. I've got to spend all this money. It doesn't matter. If your code is doing stupid things, it's just going to go very slow, just as fast. So these are the resources that basically describe the software I've talked about here. So libdnet is on SourceForge. It's Doug Song's library. The tcpdump.org guys actually maintain both libpcap and tcpdump, which is a most widely used pcap application, I think, out there. Packetfactory.net, which is the libnet site from Mike Schiffman and aka Route, is where the libnids project is stored. And Monkey is where Provost keeps his libevent code. So all these things are basically ported to OS X, Windows, and Linux and Unix, so you can very easily get them. And on my own site, you can actually download the example code here, JFlow and JScan and JTrace, to look at kind of in detail how you actually use these libraries and the stupid little things you can do with them. So you can start to think about more complex, more fun things to do with them. And finally, you got to read a lot, actually, to understand what you're looking at. Sniffing packages is a great way to actually learn how they operate. But if you can't reference them back to something else that somebody else has basically figured out for you, you're going to spend a lot of time basically reinventing the wheel. So read Stevens, Volumes 1 and 2. They're fantastic books. They're getting old, but they're still excellent books. Schiffman, who runs the Packet Factory site, has a great book describing how to use pcap, libdnet, libnet, libnids, and even more, like OpenSSL. Really great libraries, how to put them together, and fantastic tools. Good book. Highly recommend you guys get it and read it. And of course, you got to download RFCs to figure out what the heck you're looking at in these packets. You know, why is that type of service value set the way it is, for example? And what's RFC 1323? Go find out, and you'll understand way more about networking very quickly. So when you look at these packets, you figure out what the heck is going on. So I think it's a little past noon. I think I've talked for about an hour or so. I'll happily take any questions at this point, and thank you very much.